f of x equals x plus 4 times x minus 3 all over x minus 3. I've gone ahead and factored the numerator. A lot of times you'll see this problem, and the numerator will be, what, if I FOIL that in my head, x squared plus x minus 12, and then you just have to factor the numerator and realize that x minus 3 is a common factor to both the numerator and denominator. Is it continuous at x equals 3?
No.
Yeah, we could start by asking ourselves, what is f of 3? 0 over 0, it's undefined. So, nope. F of 3 is undefined. Okay, so that's an easy one. Now, if you consider the graph, if you're sketching the graph of this, the graph is almost the same as y equals x plus 4. Because when you simplify it, you scratch out the x minus 3's, and that's basically what's left, y equals x plus 4. The only difference between the graph of this function and the graph of y equals x plus 4 is that the hole in the graph. Yeah, y equals x plus 4 doesn't have any holes in it, but this one has a hole with an x-coordinate of 3. So if I'm going to graph it, I would graph, let's see, 1, 2, 3 for the y-intercept, and I think the x-intercept is over here somewhere, and at 1, 2, 3 this way. Oh, sorry. Got my 3 in the wrong place. The y-intercept is 4, isn't it? There, that's better. I'm sorry about that. Just looking at the 3 and thinking the wrong thing. So right up in here, there is a hole in the graph because at 3, it's undefined. So that's kind of what the graph of our function looks like. It's fairly easy to graph. Just put a hole that has an x-coordinate of 3 when you get there. Now, example 2, not much more difficult to graph because it's defined using the same expression. If x is not 3, and if x is 3, it's equal to 5. So there's 4 right there. There's 5 right there. That's the point. 0.35. Is this continuous at 3?
Yeah.
No, it's not continuous at 3. The limit exists. If you were going to evaluate the limit of this expression as x approaches 3, you would scratch out the x minus 3's, and you would substitute 3 for x in the expression x plus 4. You say 3 plus 4 is 7, and that's not equal to 5, though. So the limit exists, and it's not equal to what the function is defined to be. So the limit of f of x as x approaches 3 equals 7, but f of 3 equals 5, so it's not continuous. So h is not continuous at x equals 3. Is this a jump discontinuity or a removable discontinuity? Removable? Let's remove it then. Example 3, it was not good to define the function to equal 5 at 3 because the limit was equal to 7 as x approaches 3. So it would be better if we define f of 3 to equal 7. Yeah. So there we go, just like that. Let me go back to a friendlier color there. The dark blue. 7. Now, that fills in the hole. If we're graphing this, 1, 2, 3, 4, and over like that, where previously there had been a hole at the point 3,7, that fills it in. So now the graph of this function is identical in every way, including the point 3,7, to the function h of x equals x plus 4. Absolutely no difference between them, same domain, because we've defined it at 3. That was the only discrepancy. So This is just a ridiculously fancy way now of saying exactly the same thing as that. The two functions, and it's appropriate to give them the same name. It's h in both cases. Fill in the hole. We remove the discontinuity, so h is continuous, in particular, at x equals 3, and as we'll see in the not too distant future, since it's a polynomial, it's continuous everywhere. Polynomials are going to be nice. They're continuous on the set of all real numbers.